Hey everyone, the Math Lemon here, and this is my entry for the Summer Math Exposition ran by Grant Sanderson / 3 Blue 1 Brown. And today I'm going to be talking about what I like to call the Ambergram series. So let's dive right in. So what is the Ambergram series? Well, this is. Kinda. The reason why I call it an ambergram is, well, if you rotate it 180 degrees, you get the same exact shape, like an ambergram. And it's not a series in the numerical sum definition of a series, but it is simply called a series, as in a family of sequences. So we need to backtrack to what is called digital roots. So we categorize every number by its digital root. So what is a digital root? A digital root is a recursion of a digital sum. So what's a digital sum? Well, if we take n equals the digits d1 and d2, we add those digits, d1 plus d2, it equals the digit sum of n. So let's get an example of this. If we have n equals 189, we take those digits, add them up, so 1 plus 8 plus 9 equals 18. You plug that in because it's recursion, right? We take 1 plus 8 equals 9. So now we know the digital root of 189 is, well, 9. So let's play with this. So we're going to double each number and oscillate up and down. So let's take 1, double it, it's 2. So we're going to hop 1 to 2. 2 doubled is 4, jump to 4. 4 doubled is 8, jump to 8. And this is where something interesting happens. When we double 8, we get 16. So we take those digits, 1 plus 6 equals 7. So we actually go 8 to 7. Then take 7, double it, we get 14. So 1 plus 4 is 5. We go 7 to 5. Then we get 5, doubled it is 10. And I know it's insane, it's crazy, but 1 plus 0 is 1. So we go to 1. And we kind of get this kind of nice S-curve here, this nice loop. So what about 3, 6, and 9? We kind of skipped over those. Well, let's see. If we take 3, double it, we actually get 6. So go to 6. If we take 6, we double it, we get 12. So we add those and get 3. So we actually go back to 3. And what about 9? Double that, we get 18. Add those digits up, we get 9. So 9 is its own loop. So we kind of get this really interesting shape. It has this nice aesthetic, and wait, hold on. Wait a minute. Anyways, so we get this really nice shape here. And so essentially, you begin to wonder, is there more out there? Is there more to this shape? And the answer is yes. So how do you get other shapes like it? Well, eventually I discovered if you take n times 2, which is the original, and add 1, you actually get this shape. So now we can also then add 2, you get this shape, and so on. So we actually get these 9 shapes. And if you try to add more, like n times 2 plus 9, you actually get the first shape. And so it's its own loop. These shapes form an infinite loop on themselves. And so what happens now is I'm going to label each of these so that I can name them and notate them. So I'm going to call them A, B, C, A1, B1, C1, A2, B2, and can you guess it? C2. So, can these shapes interact? Can they have their own sums? Can they behave as numbers? Well, let's find out. Let's look at A here. To answer this question, we have to define it as a number somehow. And so if we look at A, there's this sequence here, 1, 2, 4, 8, 7, 5, is this kind of S loop. Then there's 3 and 6 is this smaller loop. And then there's 9 is this loop here. And then we also have to realize that these are infinite strings of these loops. So they have these infinite lengths. And this also means that we can have any of these columns here. Any of these can represent, as long as it's a 6-digit long code or something as that, we can represent A, anything here. So I'm going to call that first row the expanded notation of A. The middle one will be the mid notation of A, and all the 9s there will be the closed notation of A. So let's mess with this. So B2 plus C2. Well, 1, 9, 7, 3, 4, 6, and 2, 3, 5, 9, 8, 6. So those are both expanded notations, and we actually get a straight row of 3s. And so what does this mean? Well, if it's just one number, then that means it's a closed notation. So what has a closed notation of 3? Well, we find out it's A2. So does this hold up, though, if we try messing with the notation of both of the numbers, or any of them? So I'm going to take C2 and change out the expanded notation with a different expanded notation for C2. So that it actually gets a expanded notation, but it's still A2. Then a mid notation for A2, expanded for A2, mid for A2, expanded for A2, and so on. So no matter what, it still does equal A2, which means B2 plus C2 does in fact equal A2. And this means that these numbers do have these relationships. And when you actually look into what those relationships are, they are the equivalent to the relationships of 1 through 9 backwards. And so what this means is we can actually form a bigger shape out of these shapes. And this shape here is actually equivalent to C2 instead of A because it's backwards. But then you realize we can actually turn this into a fractal. So what we get here is kind of this infinite recursion of these shapes going down forever, right? And so it seems like it should be closed off, right? But it's not. Because you'd think that what would be just this looped off cycle of these digits, it actually allows for such a fractaline structure to occur. And so it's this beautiful pattern that can arise and be discovered, and something that no one seems to take too much notice for. And so sometimes we need to take those little looks at those things we tend to overlook. Thank you. And so next episode, I'm going to be talking about a little more of the rigor in this. And also things like the other bases, because I'm sure lots of you want to know about that. along with other ways I can present this, like this. Some of you may know this. This is a popular symbol in digit sum arithmetic. And wait, hold on. Wait a minute.